Okay, please sit down. There are still seats in the front. Okay, welcome to today's joint colloquium. And today, Dr. Yan-Ting Lin from ASIAA will introduce the speaker for us.
Hi everyone, it's my great pleasure to introduce Professor Andy Fabian from the Institute of Astronomy from the University of Cambridge. Professor Fabian got his PhD from the University College London in 1972. Soon after that, he moved to Cambridge University, and since 1982, he has been a Royal Society professor there. Professor Fabian has been the president of the Royal Astronomical Society in UK, and also was the editor-in-chief for 15 years of the leading astronomical journal Monthly Notices of Royal Astronomical Society. Professor Fabian's research covers a wide range of topics in astronomy, but he's most widely known for his work in cooling flows and also black hole-related topics. We know from simple physical considerations that in the centers of galaxy clusters, gas must cool efficiently, but we didn't observe signatures of such cooling of gas. And this is known as the cooling flow puzzle. And through Professor Fabian's and others' pioneering work, we came to realize that the black holes in the centers of these galaxy clusters may play an important role in controlling this cooling and heating. And so today, Professor Fabian will tell us about all the frontier works in astrophysical black holes. Let's welcome him.
Thank you very much. Is this on? All right? Okay. I'm having a great time here in Taiwan. It's my second visit. And thank you very much for inviting me to, first of all, go to Penghu for the astronomical meeting, and now to give this colloquium. I'm going to talk to you about astrophysical black holes. And I'm going to assume you, the audience, are mostly physicists. I see lots of astronomy friends here, but I'm really addressing the physicists. I'm going to assume, of course, that the physicists are highly intelligent, and they know a lot about theoretical black holes, but they know little about astronomical black holes and astrophysical black holes. And so what I want to do is to try and tell you about what they are. I'm going to give an introduction by showing you a little bit about the past history of black holes, why we think there's a black hole at the center of our galaxy, and then I'm going to go on to talk about this process called AGN feedback, which has very profound implications for black holes. And then I'm going to tell you a little bit about how quasars work. Okay, let's start with black holes as the history of them. Not everyone knows that they are a very old concept dating from 1784 from John Mitchell, who was actually at Cambridge University. He was a clergyman, but back then clergymen had a lot of spare time and used to do things like physics. I converted all of this to modern numbers, but the essential part of his argument is that the escape velocity on the Sun is 600 kilometers per second. The velocity of light is 300,000 kilometers per second. And he knew about Newton's law of gravitation and so forth, and then thought, well, if I stack 100 million suns together, and forget about what actually would happen, they would squash down, forget all of that, just imagine you could do that, then the velocity, the escape velocity from the surface of that object would equal the velocity of light. And therefore, how could we possibly see such an object? So he introduced the concept that there may be objects in the universe that we can't see, but nevertheless the mass would be there. It turns out that this argument gives you the correct radius for a black hole or for the event horizon of a non-spinning black hole. However, if you start to work it through and think about it, you end up with logical inconsistencies that I'm not going to go on here. And it was this guy who sorted it all out. So here is a letter dated 1913, so it's just under 100 years old, this letter, and here's Einstein's calculation of bending of light by the sun. Here's the sun, Sommer, here, and here's light coming along from here down to the observer, and it's being bent by the gravitational field of the sun. And he's saying there it's bent by 0.84 degrees. 0.84 seconds of arc. That's actually the wrong answer by a factor of 2, and it required another 2 years before the general theory of relativity, which he of course produced, gave us the right answer, because you've got to include the bending in space-time, both space and time, and that answer is twice this answer. Later, of course, 1919, Eddington did the eclipse expedition, which measured this deflection of light by the sun. Of course, it had to be done at a total eclipse. And when Eddington confirmed the 1.6 arc seconds answer, that was what made Einstein famous. And essentially, with a black hole, we're talking about immense bending of space-time. This is a sort of indication of space-time. How do you actually indicate it? Here's a two-dimensional mesh bent in a third dimension, whatever that dimension is, but you get the idea. A black hole is going to be something like that. In terms of light bending, astronomers are very commonly see light bending, and you can see, for example, in this cluster of galaxies, where all these fluffy things are distant galaxies in a cluster, you can see all these streaky things, and they are images of background galaxies where the ones that have got the same colour, probably this one, and possibly that, are all the same background galaxy, or images of the same background galaxy, where the images have been, the light has been bent by the large gravitational field of this galaxy and all the cluster around it, and all the dark matter that happens to be there. So gravitational light bending is for real. We see it. Then in terms of the bending of time, or gravitational redshifts and blue shifts, that's something which is very small. You might all remember it was first measured in Harvard in the 1950s using the Mossbauer effect, but it's now something that's important for everyday life for ordinary citizens. Here's the GPS system of satellites for satellite navigation, such as you might have in your car. There's all these satellites going around, and of course what your position is on Earth is worked out by triangulation, which involves timing how far you are from each satellite you're getting signals from. And then, of course, corrections have to be made for the motions of the satellites, but also for the fact that the clocks on the satellites are at a different altitude from the clock in your GPS system. Okay? And therefore, you have to take into account the different potential depth, and you have to take into account gravitational redshift and blue shift effects, and they turn out to be more important than the Doppler shifts. And the effect is, if you were to switch off the gravitational redshift blue shift effect, the GR effect in your sat-nav, you'll get an error of 45 microseconds per day. That actually corresponds to 10 kilometers a day. So if you went for a drive for only 2 hours, you'll be out by a kilometer. So that's the macroscopic appearance of general relativity to the general public. Well, imagine that effect. You shrink the Earth, keep shrinking the Earth, that effect would get bigger and bigger, and eventually when the Earth was shrunk to 1 centimeter in radius, it would drop within its own event horizon, become a black hole. These effects would become 100%, or, well, would become infinite redshift, and so we would have a black hole. But of course, 1 centimeter sized Earth, let's forget about that for now. Black holes, the theory of black holes, the first person to work this out in 1916 was Carl Schwarzschild, who worked out the solution for a point mass from Einstein's equations of general relativity. Einstein himself didn't think that the solutions were possible, at least simply. He found a solution within a month. He died later that year because it was World War I. He died of disease. But that's the Schwarzschild solution. Then the solution for the spinning black hole was almost 50 years later, was by Roy Kerr. I took this picture of him at the conference celebrating his 70th birthday. So 50 years from a non-spinning black hole to the spinning black hole, Roy Kerr, and now we call the solution for the black hole, we call it the Kerr solution, we call them Kerr black holes. They are, in a sense, the ultimate macroscopic object in the universe, the ultimate macroscopic particle, because they only have two quantities, mass and spin. Okay? And I guess spin for a black hole is also quantized, as is the mass, I guess. But of course, the numbers we're talking about with astrophysical black holes are truly enormous. You can have a charged black hole, but given that interstellar space is ionized plasma, it couldn't retain a charge for any significant time, so nobody in astronomy worries about charged black holes. The event horizon of a black hole is 3 kilometers per solar mass. So in order to make the sun turn into a black hole, we have to allow it to contract down until its radius is 3 kilometers instead of its current 700,000 kilometers. How to find a black hole? You've got to look for a large mass in a small radius, the Earth mass in 1 centimeter. So far, nobody's found anything like that, and we have no idea how to make such black holes, so let's ignore them. You can have sun's mass within 15 kilometers, that would be a stellar mass black hole, and such things are common in our galaxy. Or you can have 1 billion solar masses within the orbit of Uranus. So that's a really gigantic black hole. Such things do exist, and I'll talk about them. Another way to put it is you can also look for a large luminosity which varies very rapidly. The large luminosity, because material is falling into the black hole, that is the most efficient way of producing energy we know, apart from matter-antimatter annihilation, which happens very rarely. So you can get very high luminosities from these objects, and if it varies on a short time scale, from causality, it must come from a very small region, spatial region, therefore it's likely to be a black hole. So you need 1 million times the luminosity of the sun in a few if it varies in a few milliseconds. 1 billion solar luminosities in a few minutes, yes, we do see that. 1 trillion solar luminosities varying in a few days, yes, we see that. So such things are seen. But real evidence for the black hole, evidence that I think a physicist will be happy with, I think we do have it as best we can in astronomy, because remember, in astronomy we can't do experiments in the conventional sense. We can't make a black hole in the lab, then poke it and play with it or throw things at it, which is what you're used to doing. We have to make do with what's out there. This is now the centre of our galaxy. This is the plane of the Milky Way being the name of our galaxy, looking towards the centre of the galaxy in the constellation of Sagittarius. Everything in our galaxy is orbiting around a point in the centre there. We're all orbiting at around 230 kilometers per second. Curiously, roughly that's the same throughout our galaxy, all the way right down till you get to very close to the centre. But when you look at the stars right at the centre, they are doing something interesting. This is a movie, or it's a representation of a movie made by the work of 2 groups, one in Los Angeles and one in Munich, lasting for essentially the last 20 years. This star symbol is not really in the sky, but this is the centre of our galaxy, where everything's orbiting about. You see this star has already gone, this SO2, you watch it, it goes all the way round there, and it's doing Kepler's laws, and it's moving fast. That one that came in is doing fast. These ones are doing around 3,000 kilometers per second there. There's nothing in the center we can see, other than sometimes in the infrared band, you can see something flickering, and something in the radio, which is a strange radio source. This, we think, is the black hole at the center of our galaxy. by measuring the motions of these galaxies, stars, so we measure their velocities, we know their radii from the centre, means we can measure the mass at the centre. And when you do that as a function of radius from the centre, forget about the units, this is the distance from the centre, you see that mass is dropping, that's because there are lots of stars around, but then as you get to the inner part there, it starts to level out off and becomes flat. And it's because there's a constant mass in the centre. This is a rather old figure, I cannot find a better one, but the current answer is 4 million solar masses. This looks like 2.5. The correct answer is more like 4 million times the mass of the Sun. Two different groups, Genzel's group and Getz's group, agree with the numbers there. And there are now more points in this bit here, so we know what the answer is. Now, the only thing known to physics you can stick in there that will last any length of time is a black hole. If you say, well, it's actually a big group of stars, well, it would be highly luminous and the stars would collide with each other. Even a group of neutron stars would collide with each other. Even a ball of neutrinos. You can't pack them in there, degeneracy space and all that kind of thing. You can't pack enough stuff in there to actually get away with it. The density there is of where we have observations is now of the order of 10 to the 20 solar masses per cubic parsec. That's for the astronomers here. Okay, but the density is extremely high. The only thing we know we can put there is a black hole. So for an astronomer, that's proof it's a black hole. What we would like to do is to have evidence of an event horizon, etc., etc. That is yet to come. Yes. We see a flickering and flaring from this thing, and later this year, there's a gas cloud near it, which is seen to be approaching it, which may well fall, parts of it may fall into it, which is going to be very exciting. And that, so maybe within a year we'll know much more about it. What people are doing to do these observations are very fine observations using adaptive optics. The seeing of the Earth's atmosphere blurs everything, so they make an artificial star, and then they're able to use a deformable mirror to correct for the blurring due to the Earth's atmosphere. You can see the effect of turning it on compared to when it's off. And in making these artificial stars, you do it by shining laser beams up, and you make the star by fluorescence of sodium at about 70 kilometers. And this is just a movie of the two Keck telescopes looking at the galactic center using their laser beams. Of course, they're not communicating, it's just to produce this artificial star up there. It looks like they're sort of shooting down satellites or something. Now we know and we suspect that all galaxies have a massive black hole at the center. This galaxy here, M87 in the Virgo cluster, has a 6 billion solar mass black hole at the center. 6 billion times the mass of the Sun, okay, in the black hole at the center. And these galaxies, all of these galaxies do have black holes at the center. This object there's a group here who are working on this object, so I'll mention it at the end. They're very interested in this thing. I want you also to notice from this picture how spiral galaxies like our own, which look rather like that, notice they're blue. They're blue, that's because they've got star formation going on. These objects, these big fluffy ones, the so-called elliptical galaxies, don't look blue. They look orangey red, and that's because star formation has switched off. That's to do with the black holes. We now have got measurements of many galaxies in our neighbourhood, and we've got, for astronomy, a very nice correlation between the mass of the black hole and a proxy for the galaxy mass, which is the velocities at which the stars in the galaxy are moving. Probably in physics you'd like a better correlation, but for astronomy this is pretty good. It's got 4 orders of magnitude up there, and essentially it follows a nice relation. And so what we find is the galaxies where they've got, the biggest galaxies have got high mass black holes, and the smaller galaxies have got low mass black holes, and roughly the ratio is a ratio of 1,000. The black hole is 1,000th of the mass of the galaxy, or the bulge of the galaxy if it's a spiral type galaxy. And this is now looking at the ultra deep field taken with Hubble. All of those galaxies too will have black holes at their centers. Now, black holes at the center of our galaxy, one of the puzzles is why it is so faint. Actually, its luminosity isn't much more in most bands than the luminosity of the sun. Why is it so faint? Well, I'm not going to explain that. It's complicated, and we don't really know. But sometimes they are extremely bright. Now, this is not from within the black hole. It's from material around the black hole. And as it falls in the black hole, it travels up to half the speed of light, and it can liberate 10% of its rest mass energy. That makes a quasar. And this image here is showing a quasar taken with Hubble. This is the quasar. I know it's point-light because I can see diffraction spikes, diffraction in the telescope. That is a galaxy. You don't see the diffraction spike because it's an extended object. And that is a star. Now, they're roughly the same brightness, I can see from how big the images are. Okay? And these are really point sources, but the optics has blurred them out. Okay? They're roughly similar brightnesses. This is in our galaxy. This is 1,000,000 times further away. Therefore, from just flux going as 1 over r squared, that's telling us its luminosity is 1,000,000,000,000 times the luminosity of a star. So the luminosity of this quasar is 1,000,000,000,000 times more luminous than a star. Therefore, it's 10 times more luminous than all the stars in our galaxy. So these objects, quasars, in which material is falling into the black hole, can be exceedingly luminous. We can see such objects commonly, if we want to look at them, find them easily, using the X-ray waveband. On the left, we've got an optical image of the sky, showing the Orion constellation, the moon, and that's Sirius, the brightest star in the sky. On the right, I've got an X-ray image of the sky taken with ROSAT. This looks like the brightest star in the sky, Sirius, excepting this isn't Sirius that you see there. Sirius is a double star. It's got a white dwarf companion, which is a dead star next to it. That's the white dwarf companion. This is not the moon. The moon is that little thing. That is the Crab pulsar, and the remnant of another dead star, a neutron star. You can't see Betelgeuse, this red giant. You can't see it in this image. You won't find it in any X-ray telescope. Red giants don't emit X-rays. But you do see the stars in Orion's belt because they're magnetically active. But all the rest of the objects you see here, just the random ones, the bulk of them are actually distant quasars. They're black holes. If you have an X-ray image of the sky, you see dead stars, white dwarfs, neutron stars, you see magnetically active stars, and you see black holes. There are just enormous numbers of black holes out in space. Material swirling into the black hole. I now want to talk about the effect the black hole has on the host galaxy. Let me just give you some numbers. This is chemical energy. It's 5 times 10 to the minus 11 mc squared, Tn. That's the energy of TNT. It's also the energy you're generating in digesting your lunch. Okay, that's chemical energy. Then, the next most potent energy we can think about is nuclear energy. And nuclear fusion, hydrogen to helium, will give you 0.5% of mc squared. But drop material into a black hole, and you get 0.1, 10%. It can even be up to 30% of the rest mass energy can come out. That's a factor of 100 million. That's a factor of 20. 100 million, that sounds interesting. That's 10 to the 8. Okay? This is essentially the same energy density as petrol. Okay? Therefore, if your car, I don't know, imagine your car does 30 miles to the gallon. I'm using imperial units here. Then if you could run it on nuclear fusion, you could get 3 times 10 to the 9 miles per gallon. And if you could use a black hole in your engine, you could get 20 times more. But we've yet to solve the problem of getting low mass black holes. But let's just take I told you two numbers. One is we get 10% of mc squared out as energy. I've also told you that the mass of the black hole is 1,000th the mass of the galaxy. This is now going to do a very trivial calculation that when we grow the black hole through accretion, then we must release of the order of 10% of its rest mass energy. So that is around, then convert that, so m now is the mass of the galaxy, is 10 to the minus 4 of the mass of the galaxy times c squared. That's the energy that's liberated in growing the black hole by accretion. But the energy required to disperse the galaxy, unbind it, it's just the binding energy of the galaxy, is just mv squared, where v is the random velocity of the stars in the galaxy. The ratio of these two numbers, that's the energy of the galaxy to the energy of the coming out from the black hole, is 10 to the 4 times v over c squared. It's trivial, okay? The velocity of stars in galaxies is a few hundred kilometers per second, so essentially c over 1,000. So v over c is 1,000th, so put it in there and square it, I get a millionth. A millionth of 10 to the 4 is 1%. So the energy of the galaxy, the binding energy of the galaxy, is only 1% of the energy that comes out of the black hole. This is a very profound conclusion. The black hole at the center of the galaxy liberates 100 times the energy required to take the whole galaxy and send it to infinity. Okay? So a black hole can destroy a galaxy. Why are there any galaxies? Okay? Well, it could be, and probably is, that the energy that comes out as radiation, etc., can't do much to the stars in the galaxy because there's no impact. Okay, the stars are so tiny, it's not going to be pushing the stars around. What it can do, though, is push the gas around. And that's what we think AGN feedback is. The energy that comes out of the black hole, of the quasar, is actually going to push all the gas in the galaxy around, push the gas out. And it's gas that forms new stars, and if you push the gas out of the galaxy, you don't have young stars, which is why the galaxies look red and dead. The energy of the black hole, more than 100 times the gravitational binding energy of the galaxy. Okay, does this actually happen in practice? Let me take you now to show that it really does happen. This is the Perseus cluster of galaxies, which is the X-ray brightest one in the sky. What you're seeing, these fluffy things, are all in this cluster. Galaxies like to cluster. We live in a small group of galaxies. There's us, Andromeda, M33 and a few others. But this has probably got 1,000 galaxies. These are giant galaxies at the center, and basically it's sitting in a big puddle of dark matter, and also most of the baryons in the cluster are not in stars. They lie between the galaxies, and it's very hot, forming the intercluster medium. And we can see that with X-rays and make an X-ray image of it, because the gas between the galaxies in a cluster has a temperature of around 50 million degrees. It radiates in the X-ray band. So this is now an X-ray image made with the Chandra satellite, exposure of 1.4 megaseconds, and what we're seeing is the center of the Perseus cluster of galaxies. There's something going